Welcome to a brand new module, Regular Expressions, often abbreviated as regex or regex. This is a powerful and valuable topic in programming. Regular expressions provide a concise language for specifying patterns in text, allowing you to find, replace, or extract complex data in a robust way. 1. Why use regular expressions? Imagine you need to validate if a string is a valid email address, find all phone numbers in a 1,000-page document, or extract all href links from a web page. Doing this with standard Python string methods like find or split is complicated and error-prone. Regular expressions handle these complex pattern searches with a single specialized pattern string. 2. Python's real module. Python implements regular expressions using the built-in RE module. We must import this module to gain access to its powerful functions. The 4 core functions we will focus on are search, findall, match, and sub or substitute. Each of these functions allows you to apply a pattern to a string in a different way. 3. The raw string prefix, R. Regular expressions rely heavily on the backslash for special meaning. In Python, the backslash itself is also an escape character. This causes annoying conflicts. To solve this, always use the raw string prefix, R, before your pattern string, like $D3. This tells Python to treat backslashes literally, ensuring your regex patterns are interpreted correctly. To summarize, regex is essential for text processing. Our next lecture 24.02, Sequence Characters. See you there. Welcome back. To write any effective regular expression, you need to know the fundamental building blocks, the sequence characters. These are special escape sequences that let you match entire categories of characters, like all digits or all whitespace, without listing every single character explicitly. 1. Digits, \D and \D. The character \D matches any digit, which is the numbers 0 through 9. This is much shorter than writing 0 pipe 1 pipe 2 and so on. Conversely, the uppercase \D matches any character that is not a digit. 2. Word characters, \W and \W. The sequence \W matches any word character. This includes lowercase letters, uppercase letters, digits, and the underscore character. It's often used when matching names or identifiers. \W, the uppercase version, matches any character that is not a word character, which includes punctuation and special symbols. 3. Whitespace, \S and \S. The sequence \S matches any whitespace character. This includes the standard space, tabs, and new line characters. This is extremely useful for matching structured or formatted data. \S matches any character that is not whitespace, such as letters, numbers, or punctuation. To summarize, these sequence characters are your basic vocabulary for regex. Now that we know how to define simple patterns, let's learn the primary function used to test those patterns, the re.search function. We will use re.search to find the very first instance of a pattern within a string and understand the match object that it returns. Join me in lecture 24.03, Search. See you there. Welcome back. Now that we know the basic sequence characters, let's look at the most common function for finding a pattern anywhere in a string, re.search parenthesis. This function scans the entire string from start to finish and returns the very first match it finds. 1. Using re.search parenthesis. The search function takes the pattern first, followed by the string you are searching within. In our example, the pattern r \d looks for any 2 consecutive digits. The function finds 10 from 100 as it's the first occurrence. The result of a successful search is a match object. If no match is found, it returns none. 2. The match object. The match object is an essential structure that holds information about the match. To get the actual string that matched the pattern, you call the group parenthesis method on the object. You can also use the expand parenthesis method to find the starting and ending indices where the match occurred in the original string. This object is what you use to process the extracted data. 3. Handling no match. Since re.search returns none when it fails to find a pattern, the match object itself is truthy when a match is found, and none is falsy when it fails. Therefore, you may simply use an if match statement to check for success. Attempting to call methods like group on none will result in an error, so always check for a match first. To summarize, re.search is great for finding the first instance. Our next lecture 24.04, Find All and Match. See you there. Welcome back. While re.search parenthesis is great for finding the first pattern, often you need to find all occurrences, or you need to strictly check if the string begins with a specific pattern. Today, we cover 2 other critical functions, re.findall parenthesis and re.match parenthesis. 1. re.findall parenthesis. Finding all matches. If your goal is to extract every single piece of data that matches your pattern, findall is the function to use. Unlike search, which returns only the first match object, findall returns a simple Python list of strings containing all non-overlapping matches found in the entire string. This makes it perfect for data extraction tasks. 2. re.match parenthesis. Matching only at the start. The match function behaves like search, returning a match object or none, but with one critical difference. It only attempts to match the pattern at the very beginning of the string. If the pattern is found elsewhere, match will fail, returning none. This makes it ideal for strict validation, such as checking if a file name starts with a specific prefix. 3. Summary of core functions. To summarize the 3 search functions. To summarize, know your goal, search for the first, find all, or check the start. Our next lecture 24.05, Substitute. See you there. Welcome back. Regular expressions are not just for searching and extracting. They are also incredibly powerful for manipulating and cleaning text data. Today, we will explore the last of the 4 core functions, re.sub parenthesis, which is Python's highly versatile substitution function. 1. Using re.sub parenthesis for replacement. The re.sub function is the equivalent of find and replace all. It takes 3 arguments: the pattern to find, the replacement string, and the string to search within. Sub scans the entire string, finds every instance of the pattern, in our case, error followed by 3 digits, and replaces them with the string alert. 2. Controlling the number of substitutions. By default, our e.sub replaces all occurrences. However, you may use the optional keyword argument count to limit the number of replacements. If you set count equal to 1, as shown here, only the very first matching pattern will be replaced. This provides fine-grained control over your text manipulation. 3. Practical use case: data cleanup. One of the most common applications of our e.sub is cleaning up user-entered data or extracted web content. By using the pattern /s+, which we haven't formally covered but means 1 or more whitespace characters, we can replace all occurrences of multiple spaces, tabs, and new lines with a single space, standardizing the format. This is extremely useful in real-world projects. To summarize, our e.sub is the tool for automated text transformation. Our next lecture 24.06, Split. See you there. Welcome back. You may already be familiar with the standard string split method, which is limited to splitting a string based on a fixed delimiter like a comma or a space. The RE module offers a far more powerful alternative, our e.split parenthesis, which uses a regular expression pattern to define complex delimiters. 1. Using our e.split parenthesis with multiple delimiters. Standard split can only use one delimiter at a time. Our e.split can use a pattern that matches several different characters. Here, the pattern, our bracket, semicolon, comma, bracket, means split on either a semicolon or a comma. This is incredibly helpful when dealing with inconsistent data formats where separators vary. 2. Handling inconsistent spacing. This is another classic use case. If you have data where a comma might be followed by 0, 1, or several spaces, a standard split on just the comma would leave leading spaces in your output. By using the pattern our comma space star, which we will formally cover soon and means a comma followed by 0 or more spaces, we can remove the comma and all subsequent spaces in a single split operation, resulting in clean substrings. 3. Limiting the split. Similar to other string methods, our e.split supports the optional max split argument. This lets you specify the maximum number of times the split should occur. In this example, setting max split to 1 ensures the string is split only at the first colon, leaving the rest of the string intact as the final element in the resulting list. This is useful for splitting headers from bodies, for example. To summarize, you now know the 4 core functions of the RE module: search, findall, substitute, and split. Our next lecture 24.07, Quantifiers. See you there. Welcome back. So far, our patterns have only matched characters one by one. For example, \d only matches exactly 2 digits. To match phone numbers, words of varying lengths, or any sequence that repeats, we need quantifiers. These tell the regex engine how many times the preceding character or group should occur. 1. The plus sign, which means one or more. When the plus sign follows a character or a sequence, it instructs the engine to match one or more continuous occurrences of that element. For instance, the pattern \d plus will match any string of digits, such as 1, 12, or 12,345. It is non-optional. At least one match is required. 2. The star sign, which means 0 or more. The star sign is similar to the plus sign, but it makes the preceding element optional. \d star will match any string of digits, but it will also match an empty string, or where there are no digits at all. It is widely used when optional whitespace might be present. 3. The question mark, which means 0 or 1. This makes the preceding element strictly optional. It means match it if it's there, but don't worry if it's not. The question mark is useful for matching singular or plural forms, or prefixes that may or may not be present in the data. 4. Curly braces, n, m curly brace, which means specific range. The curly braces allow you to define an exact number or a range of repetitions. You can specify an exact number, like curly brace 4 curly brace, to match exactly 4 digits. You can specify a minimum n, or a maximum m, or a range n, m to match n to m times. This is perfect for fixed-length data like postal codes. To summarize, quantifiers enable you to move beyond single-character matching. Our next lecture, 24.08, Using Quantifiers. See you there. Welcome back. In the last section, we defined the 4 main quantifiers. Now, it's time to combine them with our sequence characters to build practical, real-world patterns. Understanding how quantifiers control repetition is the key to matching complex data structures. 1. Matching variable length numbers. If we want to find all prices preceded by a $sign, we can't use a fixed number of digits because prices vary. We use the pattern, our $\d plus. The plus sign here, ensures that our pattern matches numbers with 1, 2, 3, or any number of digits, but only if at least one digit is present. Notice that the $sign itself must be escaped with a backslash because it is a special character in regex, which we maybe will discuss later. 2. Matching words and spaces. To extract individual words, we combine the word character sequence \w with the plus sign. The pattern, our \w plus matches any sequence of word characters, effectively grabbing each word. If you wanted to match multiple spaces, you may use our \s plus, matching \s1 or more times, which is essential for data cleaning, as we saw with our e.sub parenthesis. 3. Matching fixed-length data, like phone numbers. For data that follows a strict format, the curly brace range quantifier is the best tool. The pattern are \d curly brace 3 curly brace hyphen \d curly brace 3 curly brace hyphen \d curly brace 4 curly brace is precise. It says exactly 3 digits followed by a hyphen, then 3 more digits, then a hyphen, then exactly 4 digits. This strictness is critical for validation and structured extraction. To summarize, you can now build powerful patterns for common text structures. Our next lecture 24.09, Matching Dates. See you there. Welcome back. Matching dates is a quintessential regular expression problem because dates often appear in many different formats. Slashes, hyphens, for-digit years, two-digit years, and so on. This lecture shows you how to combine sequence characters and quantifiers to create flexible and accurate date patterns. 1. Matching a simple fixed format. For a strictly formatted date like month/day/year/year, we use the fixed-length quantifier (n) and the digit sequence \d. The pattern are \d \2 /d /2 /d /4 exactly specifies 2 digits, followed by a slash, then 2 more digits, and so on. This is precise but lacks flexibility. 2. Matching multiple delimiters and year lengths. When the format is inconsistent, we need flexibility. We introduce the character set inside square brackets /hyphen, which means match either a slash or a hyphen. We also use the range quantifier (1, 2 for the month and day, allowing 1 or 2 digits. Finally, the year allows for either 2 or 4 digits using (2, 4). This significantly increases the pattern's versatility. 3. The greedy nature of quantifiers. A key principle in regex is that quantifiers like +, $, and the range quantifier are greedy by default. This means they match as much text as possible while still allowing the entire pattern to succeed. For example, \d+ will match all 5 digits in 10000, not just the first one, because matching 5 digits satisfies the one or more condition while consuming the maximum number of characters. To summarize, you can now build sophisticated patterns using the tools we've covered. Our next lecture 24.10, Special Characters. See you there. Welcome back. So far, we've used sequence characters like \d and quantifiers like +. Now, let's look at the remaining special characters that control character choices and define boundaries, allowing you to create truly sophisticated patterns for validation and extraction. 1. Character sets, square brackets. Any character placed inside square brackets means match any single character within this set. We saw this when matching dates with slashes or hyphens. You can also define ranges. For example, square bracket (z) square bracket matches any single lowercase letter. If you place a caret sign, immediately after the opening bracket, it means match any single character that is not in this set. 2. Or operator and any character. The pipe sign, acts as the logical or operator, allowing you to match one complete pattern or another complete pattern. This is different from character sets, which match single characters. The dot sign, matches any single character except the newline character by default. This is often used as a placeholder. 3. Anchors, $, and $. These characters are called anchors because they do not match actual characters but instead match a position. The caret sign, matches the position at the start of the string. The $, matches the position at the end of the string. Using both $pattern $, is the definitive way to validate that an entire string conforms to the pattern, not just a part of it. To summarize, these special characters give you surgical precision over your matches. Our next lecture 24.11, Using Special Characters. See you there. Welcome back. In the last lecture, we defined the special characters that form the structure of advanced regular expressions. Now we will combine anchors, character sets, and the OR operator to build a robust pattern for a common validation task, checking for a simple email address. 1. Building the username part or local part. The first part of an email address before the @ sign typically consists of letters, numbers, and maybe some punctuation like dots or underscores. We use a character set, square brackets, to define the allowed characters, a -z, a -z, 0-9, and the dot, and underscore. Then we apply the plus sign quantifier to ensure that this local part has one or more of these characters. 2. Building the domain name part. After the @ sign, we have the domain name, like gmail.com. This is similar to the local part, but often separated by dots. The pattern we use, square bracket a -z 0-9 plus, ensures one or more allowed characters for the main domain. This is followed by a literal dot, /dot, which is required because the plain dot is a special character, and then another set of one or more allowed characters for the top-level domain, like com. 3. The complete validation pattern. We combine the local part and the domain part with a literal @ sign. Crucially, we wrap the whole expression in the anchor characters, the $sign, at the beginning, and the $sign, at the end. This ensures that the pattern matches the entire string, not just a small piece of text within a larger invalid string. This is the difference between extraction and strict validation. To summarize, you now know the key components of regular expressions. Our next lecture 24.12, Web Scraping Demo. See you there. Welcome to the final lecture of our regular expression section. To conclude, we will tackle one of the most practical applications of regex, extracting data from unstructured text, specifically HTML, a process often called web scraping. We will see how to use the components we've learned to pull out links and titles. 1. Defining the target data. Let's assume we have a simple block of HTML containing a few anchor tags, href tags. Our goal is to extract the href value, which is the link target, and the text between the opening and closing tags, which is the link title. We will use one powerful pattern to extract both pieces of information simultaneously. 2. The extraction pattern. This pattern may look intimidating, but it's just a combination of concepts we've learned. The parentheses, around the link value and the title text create capturing groups. When you use our e.findall parenthesis with capturing groups, it returns a list of tuples, where each tuple contains the strings matched by those groups. 3. Executing the extraction. When we run our e.findall parenthesis on the HTML using our pattern, it successfully extracts a list of tuples. The first element of each tuple is the href link, and the second is the text title. This shows the power of combining quantifiers, character sets, and capturing groups for complex data extraction like web scraping. To summarize, you've mastered regular expressions, a highly valuable tool for text processing. Our next module shifts focus entirely to managing and manipulating time, which is critical for logging, scheduling, and performance measurement. Our next lecture, 25.01, Date and Time. See you there.